All right, so the hydration reaction of an alkene is also known as electrophilic addition of water, and so that's the next thing we're going to do. But we want to remind ourselves what that electrophilic addition of HX was and what those products are, so that way we can complete this chart. And so remember, addition of that proton was at the secondary position in this case because we formed that tertiary carbocation, which then allows us to get the addition of that X nucleophile, and that can be either it's going to be syn or anti because of that carbocation intermediate. You have a planar carbocation, and a nucleophilic attack from the top or the bottom is equally possible. So now we have water and acid. Okay, so acid is in this case it's going to be an acid, and then water is going to be our nucleophile. We also have another nucleophile that is our alkene, and what that does is it attacks the proton in a similar fashion to the HX reaction. And so what do we get after that? Well, we get the same carbocation intermediate, right? We've seen this before, so this reaction shouldn't be too difficult to follow. Okay, so same step as HX addition. And now, since we don't have a nucleophile in our conjugate base, we do have water present. And that water can attack from the top or the bottom, again, just like the halogen did. Okay, and then we will get a an oxonium intermediate because water has obviously those two protons on it. And then let's see, we got the one oxonium here, and then we got the other oxonium here. Okay, so after the loss of the protons, it could be either some base, whether it's the conjugate base of sulfuric acid, or it's water. Okay, water is much better base than hydrogen sulfate. So there you go. Remove that, you neutralize it, and then you get your two different products. And notice the similarities not only in the mechanism but also in the products. We have syn and anti addition of that new nucleophile OH, giving us these two different products here. Okay, so if you have an acid, you'll want to protonate something, right? So that's really what you're going to look for first. We always have to remember that the pi bond is an abundance of electrons and is a nucleophile. Okay, so let's go ahead and just paste that here to help complete our chart. Okay, now what we can do is move on to halogenation. Okay, and let me just make a note for you real quick. Same as above, just different nucleophile. Okay, just as a reminder. Also, do not forget that Markovnikov addition of that nucleophile means that the nucleophile is going to the more substituted position, while the hydrogens are going to the least substituted position. Or the hydrogens are going where more of the hydrogens are. Okay, since it does have that carbocation intermediate, we also want to remember that rearrangements can occur, and then of course the syn and anti addition that leads to the two different products. Okay, and that's just because we have that planar carbocation intermediate. Okay, again, just a reminder for you, but helpful always to get that reminder, right? Another thing about this hydration reaction is that it can be done not only just with water but with an alcohol as well. Obviously with some limitations, but we don't need to get too crazy. Let's just try methanol. We're gonna get an OME in the syn and anti addition portion. Okay, so remember ME just stands for methyl. So MEOH is methanol. All right. Now, sorry, let's get back to the halogenation now. Okay. This one is nothing even close to the first two. Okay. So so pay attention. Basically, it's weird, but it still makes sense. Okay, so addition of the halogen, and we're really only adding chlorine and bromine. Okay, we're not using iodine or fluorine. Okay, so that's what X represents here, and we are adding two X's across that pi bond, and so we obtain a vicinal dihalide. Hopefully you know why this particular synthesis would be useful, but because obviously with vicinal dihalides, if we have multiple beta hydrogens, we can create an alkyne. So obviously, in addition to that, though, we always have that anti-addition. So here's the weird part. Nucleophile is still the alkene, but the halogen is going to act as that electrophile. One of them is, and then also a nucleophile. So what these arrows represent are the pi bond attacks the X, and then the electrons, the lone pairs from that X, also create a bond with a carbon. And what you end up with is a halohydrin intermediate. Okay, so this is a positively charged halogen, and it's very similar to an epoxide. And then that X can attack just like normal as a nucleophile, and then it pops open that strained, so you remember ring, that halonium ion, and you get your anti-addition to get your vicinal dihalide. Okay, so all right, let's think about this. So it works with, again, chlorine and bromine. Chlorine, you'll obtain that chloronium ion, and then the bromine, you'll obtain the bromonium ion. Okay. Now, again, this is similar. You can think of them as like epoxides, right? And so you should think of them like that. But not only epoxides, but maybe, well, it depends on the reaction, but epoxides in the presence of good nucleophiles, or with acids and like weaker nucleophiles, were two different types of reactions, right? So I'll just kind of throw that in there for now, and then we'll take a look at it later, but when that comes up. So it must be backside attack, which leads to anti-addition. There's no syn addition because there's no carbocation intermediate. Okay, so because we have that halonium ion forming, there's never a carbocation intermediate, and so we have to get backside attack, because you can't have two halogens approaching from the same side. That's too much electron density, and there's going to be too much repulsion. Okay, so it's essentially an SN2, just like we might see in an epoxide reaction, right? So this is my attempt to draw the mechanism with a different view, kind of more like a side view of that ring. So once the alkene attacks the bromine, we form this bromonium ion, and this is really what it looks like, right? So it's projected up above the ring, okay? And that means we can't attack from the top. The easiest place for this bromine to attack, or bromide to attack, is from the bottom. There's nothing going on the bottom. There's hydrogens there that I didn't draw, but there's just not much in terms of electron density or sterics, okay? So that red arrow approach, that's going to yield one product, and the blue arrow approach is going to yield another, okay? So the red one first, since we're breaking that bromonium ion, and bromine's going to the left on the top, we have the bromine on the right on the bottom, okay? And now for the blue arrow, that bromonium ion is kind of breaking on the left side and moving over to the right side, so we have this dihalide here. Okay, so what's the relationship between these? Well, here's my gorgeous mirror. These are mirror images of one another, right? And if you were to try and flip it, you would actually obtain the same exact looking molecule. So these are superimposable mirror images of one another, which is enantiomers, right? Cool stuff, cool stuff. You can also draw them like this, just so you know. If that bromine's down, it's a dash. If it's up, it's a wedge. Okay, so then we got a wedge and a dash on the other side. if that's easier for you to identify the relationship, do it that way too. It's all good. All right, so now let's take a look at that methyl cyclohexene and see what we would get for our halogenation reaction. So let's use bromine or chlorine, but I'll use bromine in the product. So we're going to get a wedge and a dash here. We got the bromine and the dash, and they got the bottom bromine as a the trans wedge. Okay, so if you draw one, just immediately give the other bromine the opposite sign. So this one's a wedge, that means the other one's going to be a dash. And you don't even have to think. You know that they are always going to be anti to one another. Okay, just because of the mechanistic pathway. So I'm also labeling the two bromines, blue and red. And if you think about it, doesn't really matter what you assign as a nucleophile. Either way, you're going to get the same product. So if the bromide attacked the least substituted, it could attack from the bottom or the top because the bromonium ion can approach from the top or the bottom. So it doesn't really matter. All right. So let's talk about stereospecificity. I don't really care to label things as like regioselective or stereospecific or things like that. It's nice to know, but like, who cares, I guess? Like, cool story, bro. Just know the mechanism and you'll get the same outcome whether or not you knew it was stereospecific or regioselective or an antioselective, like whatever, right? So let's try these. This is a cool topic though. Like, the outcome of this is really interesting. So we've got the trans dihalides, right? The trans vicinal dihalides are the product of this cis alkene. Okay, so what's the relationship between them? Let's take a little look, see? Okay, so we've flipped this thing and reverse it. Okay, about this axis right here. This is the axis of rotation. That puts the molecule looking like this, and you can see that these are clearly not the same. They're non-superimposable mirror images, which is enantiomers. Okay, so let's take a look at the trans alkene. Is this going to be different? Okay, well, we got the wedge and the dash, i.e. the trans vicinal dihalides here. Now, that's at least the, I guess they're the anti-products, right? So they are, this is after the anti-addition occurred. If we rotate about this axis right here, this vertical axis like above, it's not really helpful because it doesn't put it in the orientation that we can kind of compare, right? So what we want to do actually is rotate about this bond right here, okay? This carbon-carbon single bond, and that way it puts it more or less in the same orientation as the cis one. Okay, so what that does though is that you can see that we have wedge and dash for the products. And all you have to do now is rotate about that vertical axis and you get the same exact products. So they're identical mesoisomers. And that's what's cool about this, because the cis isomer, cis alkene, yielded enantiomers, while the trans yielded the meso compound, which is our identical compounds. This is crazy, right? Mind blowing. Super cool. So just put an asterisk by that one for sure. So we've got an alkene here. Let's see what the product is, right? Anytime you draw one alkene on that one chlorine on that carbon, you just give it a wedge, and then you give the other one a dash, and then you draw the other compound. So it's like really easy to draw the compounds. So in terms of like memorization, super easy, right? But you really want to understand the mechanism so that you can really deeply understand it and why things happen. That way you can kind of answer more or less all of the questions no matter how I ask them. Okay. All right, so we've got this trans compound right here. of course, we can abbreviate that benzene ring with a pH. That's what I'm doing here. And we just did a problem like this, right? So what is this going to yield? It's going to yield mesoisomers, identical compounds, 2 adams, and there you go. Don't forget the definition of mesoisomers too, by the way. So that's when you have 2 stereogenic centers, or at least, and then it's still achiral because of that plane of symmetry. Okay. So now we get to fill out another part of our chart. Come on, fill out your chart. Do 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 do. I don't know the words. I would really want you to try and figure out what sitcom that was. All right, so we get anti-addition, right? Bada bing, bada boom. And now we get to move on to this one, X2 and H2O. So that's called the Halohydrin Formation. Halohydrin Formation. What do you think that stands for, right? A halogen and like hydration, right? So that's water. So we're adding, oops. All right, we got an alkene. So what is this really going to look like? The product, we're going to add one component, which is the halogen, and the other component, which is the water. And we're going to add it in a similar fashion to other reactions, right? In that anti-addition, but we're only adding one X and one OH. Okay, and so the cool thing is that the first step of this is very similar to, or is exactly the same as the halogenation addition reaction, and we form that halonium. And now water is going to serve as our nucleophile. And after the loss of a proton, we end up with our halohydrin product on the right. Okay. Now, again, this halonium ion, this is, again, similar to an epoxide reaction, right? But not only is it similar to an epoxide reaction, it's going to be similar to the one where we added the acid and then maybe with water as the nucleophile. And so remember the details for that one where the water attacked the more substituted carbon, right? And you can think of it as that's the more stable carbocation intermediate if it were to pop open, but and more or less it's the more stable position in the transition state. Okay, so this is the product that we get for the methyl cyclohexene reaction for the halohydrin formation. Okay, so let me draw the wedge and the dash. We're still going to get the 2 isomers because remember anytime you form that halonium ion, that can form on the top of the ring or the bottom of the ring because it doesn't matter. It's just statistics, right? So 50-50 from top and the bottom. Okay, so sorry, let me draw this ring from the other view so that way you can kind of see it. And more or less how the halonium forms, or in this case the chloronium or bromonium ion, I guess, huh? Whoops. All right, so we've got our chloronium ion here, and we've got that's projected upward, but our hydrogens are down. Okay, so water can approach only from the that's supposed to be a methyl. My bad. Water can approach only from the bottom because of that chloronium ion occupying the top portion, and it's going to attack the more substituted carbon again because that's going to allow you to achieve that most stable transition state. Again, because in the transition state, the positive that carbon is going to bear some form of the positive charge, and it's more stable at the tertiary position. So that's it. After it attacks and we lose a proton, we end up with the the halohydrin on the right. Okay. Now, how do we get the halohydrin on the left of that? Okay. So let me draw this terrible drawing again. I'm trying. I'm not an artist. I kind of am an artist, but I'm not the best artist. We got the chloronium ion projected downward. That's what I meant, where you can get the chloronium ion on the top or the bottom of the ring. Now we're still attacking that least substituted carbon, so we get the OH at that tertiary position anyway, but we got it as a wedge now, and so that's how we get our two different products. Okay. And of course, the tertiary carbon can better stabilize the carbocation in the transition state, and that's pretty much. And it's not a full straight up carbocation; it's delta positive, but you get the idea, right? Same as the epoxide reaction when we were adding acid and water, for example. All right, so another source of bromine is NBS. So NBS is also called N-bromosuccinimide. That's what the NBS stands for, and it looks like this. And really all you need to know is that it's a source of elemental bromine, Br2. So if we have bromine with water, then we're going to form a halohydrin. Okay. Now, that's pretty much it. You don't really need to know the mechanism as to how that elemental bromine is formed, but you do need to know that NBS with water, and then DMSO. So DMSO is the solvent in this case, and that's also needed. It's a polar aprotic solvent. We saw this in the substitution reaction and elimination reactions chapter, and so that's it. We're still going to yield the halohydrin with the OH on the more substituted position, because really all we're doing is introducing bromine. Okay, and that bromohydrin is formed, and then this chlorohydrin is formed up above. I don't know if I didn't mention it before. Sorry, but we're making halohydrins, but we can be more specific and specify the hydrogen or the halogen. Okay, pretty straightforward though in terms of nomenclature. All right, so the reminder for this particular reaction, just like the others, I want to remind you that there's no rearrangements because we don't have a carbocation intermediate. The OH ends up at the more substituted carbon. Just said why, okay? And it's anti-addition, which is really just going to lead to trans products, at least with respect to the nucleophile that attacked and then the electrophile that was added, i.e. the halogen, okay? Now, we get to fill out our chart. Come on, fill out your chart. Do. I really got to learn the words to that. All right, so here we go. We've got our OH at the more substituted position and the X in the anti or trans position with respect to the OH, and then vice versa. Boom. Boom city. That's it for that one. It's, if I'm moving quickly, it's because it's really like the same thing over and over, right? Really what you need to focus on is make sure you understand which is the electrophile and which is the nucleophile, and there you go. That's it. Understand the mechanisms. Okay, don't just memorize this stuff. All right. Let me know if you have any questions.